All right. Happy snow day, everybody. We are going to talk about two things. I'm going to go ahead and record them. That way, everybody that, everybody, since nobody's coming to class tomorrow since I canceled, everybody will be able to get the same instruction. Now, if you have any questions, you will have to email me them or talk to me about them on Thursday or whenever we're back in school, depending on how much snow we get. But I wanted to make sure that we all had the instruction and we didn't fall behind. So we're going to start today with a review of the QG vorticity equation. Now, we did talk about this last semester, and that material is still up on Canvas. Now, obviously, it's last semester's Canvas, but just because I know we don't all remember it, we will start it again. So, QG vorticity. So, this is our agenda for this one. We're going to do an introduction, then we're going to talk about some assumptions that we make for the QG approximation. We're going to talk about the QG primitive equations, like the equations of motion, thermodynamic equations, etc. Then we'll talk about geostrophic relative vorticity, and then we'll make our QG vorticity equation. Now, you may have noticed I have an agenda at the beginning of all my lectures. The point of this is to guide your thinking about these equations. I want you to see how we build these equations, and then when you look back, you should be able to look at this slide and remember the basic steps that we did to build these equations. So, introduction to start. And no, I did not change any of the clip art. I was tired. All right, so a Rossby number. Let's remember Rossby number. That's acceleration over our Coriolis. So acceleration is our u squared value, or our horizontal velocity scale, over our length scale. And then that's over Coriolis, which is our f naught times our horizontal velocity scale, which simplifies to u over f naught times L. For our synoptic scale motions, we agreed that u is about 10 meters per second. That's a normal wind speed, right? L is 10 to the 6th meters, also normal for our large scale weather systems. And then our f naught is 10 to the negative 4th. So our Rossby number for mid-latitude synoptic scale motions is 0.1. That means if we have a 0.1, that's a geostrophic motion, okay? It defines geostrophic balance, right? The balance between horizontal pressure gradient force and Coriolis force. So this is our equation where that G potential symbol is gravity times height. Our horizontal gradients of Z on an isobaric, that's a constant pressure surface, correspond to our horizontal gradients of pressure on a constant height surface. So it's kind of a flip-flop, right? Our horizontal pressures of height on a constant pressure surface are similar to the horizontal gradients of pressure on a constant Z surface, right? We can decompose the wind into geostrophic and ageostrophic components. A reminder, ageostrophic just means non-geostrophic, right? So any wind is made up of geostrophic and not geostrophic components. Not that hard, right? So we just use VG as geostrophic and VAG as ageostrophic. Again, that prefix A, if you see it in front of anything, it means not. So ageostrophic, not geostrophic. Let's talk about geostrophy. So there are some few things that we need to know about geostrophy. We assume that along flow accelerations are neglected in geostrophic wind, and therefore any along flow accelerations are associated with the ageostrophic, the not geostrophic wind. Therefore, we can state that the ageostrophic wind is much, much smaller than the geostrophic wind. So that if we divide it by the geostrophic wind, it's basically zero, right? If we divide a small number by a much, much, much bigger number, it's approximately zero. So we're going to talk about some QG approximations. There are three key principles. The first of which is advection is mostly horizontal and dominated by the geostrophic wind. We're going to use our total derivative to represent that. It does not contain any vertical motion terms because those are associated with ageostrophic motion, and geostrophic motion is non-divergent. It's non-divergent, which means there cannot be any vertical motion. So those vertical motion terms that contain omega or z or dp are not in this equation. All right? Second, the Coriolis parameter at any given latitude, that's our latitude marker now, theta naught, can be expressed in terms of a constant value f naught plus a small perturbation that's based on the product of the local meridional variability in F and the physical distance from your reference latitude. You'll see that as plus beta y is going to be that perturbation, where beta is the change in the Coriolis parameter in the y direction. It's equal to 2 omega cosine of the reference latitude divided by a, where a is Earth's radius. Not that hard. It's an order of magnitude less than f naught. So really, Coriolis isn't changing that much, but it's enough that we want to make sure we're using the correct latitude in our equations. We did this some last year in some of the labs, so this should be review. If we substitute f with f naught, that makes that geostrophic wind non-divergent. Again, if it's non-divergent, divergence leads to sinking motion, convergence leads to rising motion. So if it's non-divergent, it also means non-convergent. That means there is no vertical motion. Our third assumption is that it's localized in time and space. Vertical temperature perturbations are negligibly small. So if we look at how temperature changes in a vertical profile in time and in space, that temperature profile should remain mainly the same over time and around areas close to it. Should remain pretty much the same. Any changes should be pretty small, and we don't have to worry about them. Those are our three key geostrophic principles. Now we're going to talk about some primitive equations. That is horizontal momentum equation, our vertical momentum equation, our continuity equation, and our thermodynamic equation. We don't really need these for the QG vorticity equation. So I know you're going to think, well, why the hell are we doing them? You need them for the QG omega and the QG height equation. We will talk about QG height equation this week. The QG omega equation will be the next time that we have a lecture. So let's talk about horizontal momentum equations first. For pure geostrophic flow, horizontal momentum equations simplify to geostrophic balance. But our atmosphere is never exclusively geostrophic. If it was, there'd be no clouds, there'd be no active weather. But that's what actually happens. We have clouds. I'm looking outside right now. We've got some clouds out over the lake, so I know that assumption's not true. So we know that advection, so movement by that A geostrophic wind and changes along the flow are small, but they're there. So here's our equation. Should be pretty similar to what we already were doing. You have that F, it being the reference latitude approximation, where you have F naught at the Coriolis at the reference latitude plus your perturbation, your beta term. And then notably, we have this friction term here. Friction is really only going to be important at higher levels, at lower levels. It's negligible at higher levels, but we do have it in this equation. So you'll notice I've just taken this and moved it here. The left-hand side of this equation, this part right here. Sorry, I'm realizing that I'm on the wrong screen. Let me go back. This equation is this equation here. I've moved this down here. This simplifies this complete derivative. We can unpack that into our local derivative, where we just stand still and we let the flow move around us, and we can pack it into our partials. That unpacks into this. Again, our geostrophic wind is non-divergent. There's no vertical motion, so the advection term is only two-dimensional. Sometimes you'll see that DDP. The DDP is not in there because that's a vertical derivative. We're not talking about vertical motion, so it's gone. Let's talk about the right-hand side. All right, our right-hand side describes three forcings that change the geostrophic flow. Two are related to Coriolis. That would be this one and this one. And one's related to friction. That would be this one. Our first term indicates the ageostrophic wind can change the geostrophic wind following the motion. So you'll see this AG here, VAG, that's the ageostrophic wind. That's in our horizontal momentum equation for a VG, so that we know that it can change the geostrophic wind following the motion, as in dt, that complete derivative there. The second term indicates that the meridional variation in Coriolis force can change the geostrophic wind. So we had that beta term. Remember, that's dependent on Coriolis. Beta dF dy, where F is that Coriolis force. Note that a standard Coriolis term, our normal F naught term, and pressure gradient force are forcings that define geostrophic balance. We've seen those in all of our equations, but they don't show up in this because this equation is for change in geostrophic balance. It's not an equation for geostrophic balance. We're talking about how does it change? Well, the answer is changes in Coriolis force and changes in a geostrophic wind, and then friction, right? What is friction going to do to the wind? It's going to slow it down. When friction slows down the wind, it's no longer in geostrophic balance. So that can change the geostrophic wind as well. All right, let's talk about vertical momentum then. Our vertical momentum equation is given by our hydrostatic equation. Why is it given by our hydrostatic equation? When we're in hydrostatic balance, there's no vertical motion. Our upward pressure gradient is balanced by gravity, and there's no motion. That's right, because in geostrophic balance, there is no vertical motion. So we can use our hydrostatic equation. We don't need a new one. This is another way of saying our synoptic scale vertical motions of our small magnitude. Yes, there is vertical motion, but it averages out, right? So we're just using our hydrostatic equation. All right, continuity. You guys better remember the continuity equation. I hope you remember the continuity equation. If not, go back and look at the PowerPoints. It's one of our most important equations. This is just the exact same equation you're used to, except you'll notice that it's the geostrophic component and not the geostrophic component. Otherwise, it's the exact same equation. It's written a little differently because you see this gradient operator, but it's the same equation. All right. But we're using the geostrophic component because only the geostrophic wind is divergent or convergent. The geostrophic wind is non-divergent. If you take one thing away from this lecture, I hope you remember the geostrophic wind is non-divergent. And we need geostrophic wind for synoptic scale vertical motion. So that's why we have this VAG instead of VG, or total wind. Okay, that's the biggest difference here in our continuity equation. Thermodynamic equation. Here's this. SP here is our static stability, and dQ dt is the diabatic heating rate. So here's all of our terms. We have our local temperature tendency. So T here is temperature. How is that changing in time? If we're at the same spot, we're not going with the flow. Then we have this horizontal advection of temperature by the geostrophic wind. So here's the temperature, and here is the geostrophic wind. You'll notice that G subscript. Then we have our adiabatic warming and cooling. So adiabatic warming and cooling reflect temperature changes that are associated with vertical motions under adiabatic conditions. We can assume a statically stable atmosphere where the potential temperature increases upward. So think like an inversion on QT if you're familiar with that. So then SP, our static stability, would be positive definite, which means it's always positive. So dry adiabatic ascent, omega is negative because we're ascending, results in an air parcel cooling, right? That ddt is going to be less than 0. If omega is negative and SP is positive, that makes that term negative. ddt is positive. Sorry, negative. I don't know what I just said. Negative. By adiabatic expansion, right? Dry adiabatic descent omega is positive, SP is still positive. That results in an air parcel warming, right? ddt greater than 0 by adiabatic compression. Though vertical motion is typically small on the synoptic scale, consistent with the geostrophic wind being small. Remember, geostrophic wind much smaller than the geostrophic wind, so it was like 0 if you remember that earlier in the PowerPoint. Vertical motion is also small because of that. This term can't be neglected because the static stability typically pretty large. So we still need this. All right, let's talk about geostrophic relative vorticity. So you should remember our relative vorticity equation. We're just going to make it geostrophic. We already did this. Again, this whole PowerPoint should be review. I'm presenting it in a little bit of a different way than I did last semester to try and make sure all of those gaps are filled. But if last semester made more sense, that's totally fine. Those PowerPoints are still up. If this semester makes more sense, great. You've already been exposed to the material once. Hopefully the second time really helps nail it. All right. Geostrophic wind on isobaric surfaces. So here's our U wind and our V wind. You'll notice this the G, the subscript of G means it's geostrophic. And then our relative vorticity equation is normally dV dx minus du dy. All I'm doing here is adding the subscripts of G. That's it. That's the only thing that's changing for geostrophic relative vorticity. And then we can use our definitions of UG and VG and plug that in here. So you'll notice like ddx, that's right here. And then our definition of VG would be this one, that's here. And then our definition of UG is this, and that's here. We can rewrite that in this way. I know it looks scary, I promise it's not. You'll understand it when you start using it. If you know the geopotential, that's this. On an isobaric surface, you can obtain the geostrophic relative vorticity and the geostrophic winds. And if you know the geostrophic wind, and therefore the geostrophic relative vorticity, you can obtain the geopotential. That concept's known as invertibility. We will use that a few times later in the semester. So, some key concepts. Geostrophic relative vorticity is maximized, cyclonic, at the base of a trough on an isobaric surface. So, at the base of a trough, the bottom of a trough, geostrophic relative vorticity is maximized. It's cyclonic, right? Because it's going counterclockwise around the low in the northern hemisphere. That's cyclonic. Now, I want you to remember, in this case, I'm just talking about vorticity. I'm not talking about vorticity advection, as we did in the QG omega equation. Just talking about vorticity. Geostrophic relative vorticity is minimized, or anticyclonic, at the apex of a ridge, right? We're going clockwise. In the northern hemisphere, that's anticyclonic. Vorticity is minimized or negative at that apex of a ridge on an isobaric constant pressure surface. So note here this del operator, that's that Laplacian, and that P subscript denotes that it's computed on an isobaric surface. That finds the maxima, remember I'm talking about maximized, and minima, minima are anticyclonic. That's what our Laplacian here, our second of the del operator, that second derivative built into that del operator, that's telling us that we're finding the maximum minima. Why do we care? I feel weird not having any of you guys talk back to me. The evolution of geostrophic relative vorticity, both in time as well in space, can provide vital information that can be used to diagnose the movement of synoptic scale meteorological phenomena and the synoptic scale vertical motion associated with phenomena. We use this to determine the formation, the motion, and evolution of mid-latitude cyclones. So you've already talked about QG omega. We will talk about it again, but today we're going to talk about QG vorticity and QG height, and we can use that to figure out the movement and intensity of troughs and ridges. Our wave pattern, also known as the storm track. So we're going to talk about the QG vorticity equation. So here's how we make any vorticity equation. You're going to do negative ddy of the x momentum equation and positive ddx of the y momentum equation. That's how you make a vorticity tendency equation. Now remember, tendency here, that means how is vorticity changing? How is it changing as time goes on? Here's how you do that. So if we do that to the QG equations of motion, here's our QG equation of motion, here's our x1, and here's our y1, and then we're going to take the derivative with respect to y of the x1 and the derivative with respect to x of this y1. That first equation expands to this. You have to be careful, all right? Beta, that beta term, it's constant with respect to y, and so is y naught. But y is not constant, and VG isn't. That second equation expands to this. All right. Now, there's a bunch of simplifications that can happen here. So here's those two equations stacked on top of each other. If you want to go through and find all the simplifications, be my guest. They are on my other PowerPoint. But if you don't want to, here's what it simplifies down to. Here's that relative vorticity, geostrophic relative vorticity, you'll see. And then here's our ageostrophic component. You'll see that as well. This is technically the QG vorticity equation, but we can rewrite it to make it even more useful. Here's our final one. Here's our final form. Term 1 on the 2 on the right-hand side. So actually, let's start with the left-hand side, right? This is saying, how is geostrophic relative vorticity change with time? Vorticity, tendency. So you'll see I've written QG vorticity equation. When we're talking about a QG vorticity equation, we mean QG vorticity tendency. I talked about that a little bit last semester, the naming nomenclature, what we were using, but just want to rehash it. QG vorticity is equal to QG vorticity tendency equation. We're not that super strict about it, so sometimes it can get confusing, but that's how it is. All right, so this tells us that it's a tendency equation. We have that time derivative. So first term on the right-hand side, we have this beta term, and this one, we also have this geostrophic relative vorticity term in the x direction by the u wind, right? This is our geostrophic relative vorticity advection. Hold on, sorry. And then we have our planetary vorticity advection term, and then our stretching term. So do you remember our stretching term from the vorticity tendency equation? The main one from last semester? It's still here. You'll notice that with our vertical motion, right? That's our stretching term. But all of our friction terms, our tilting terms, your favorite, our solenoidal terms, those have all been ignored or scaled out in QG. That's how geostrophic relative vorticity changes for QG motions. Geostrophic wind, UG, VG, can advect more or less, relative vorticity. The north-south geostrophic wind can advect more or less planetary vorticity. So I'm sorry, this is actually messed up. That's why I got confused. This should be term 1. This term right here is the planetary vorticity, and these two are the relative vorticity terms. That's why I got super confused there for a second. I'll try and fix that and re-upload it. But for now, if you see this, that's the relative vorticity, right? So obviously these two are the relative vorticity advection, and then this is the planetary vorticity advection because it has that beta. Remember that beta term includes the Coriolis force, which is a proxy for our planetary vorticity advection. And then this is still the stretching term. You can think of like a figure skater, and you pull it in, you stretch it out, and it spins up faster. And if you put your arms out, you diverge, it spins slower, right? Okay. That vertical motion can stretch or it can squash the spin. Vorticity is just spin. All right. I know that was a lot. Don't freak out. Vorticity is spin. How is the spin changing? You can push more spin into an area, then that area has more spin. You take spin out of that area, you push less spin into the area, there's less spin in the area. That's it, basically. Or you can stretch the spin that's already there. That's how it changes. That's it. It's really simple. And most of the time, you're not going to be asked to calculate this. You're going to be asked to look at a map and remember these terms and be able to think qualitatively, not quantitatively. All right, let's do the next one. Flying through when I don't have questions, but that does mean you probably are going to have questions and you should email me them. All right, QG height tendency. Here's our agenda again. Remember the purpose of that. We're going to talk about QG vorticity first. How do we get from QG vorticity, there's a reason we did that one first, to geopotential tendency. Then we need the QG thermodynamics equation. We already went through that in the vorticity, but I'll do it again. We'll solve for geopotential height. Then we'll get to the height tendency equation, and we can talk about the different terms. And then we'll talk, why are we even here? Why are we here? I don't know, man. I guess we'll have to figure it out. All right, QG vorticity to geopotential tendency. we can express our geostrophic wind in isobaric coordinates as this. This should look very familiar. It was just on the last PowerPoint. And then we can use hydrostatic balance to convert from pressure gradients on a height surface to geopotential gradients on a pressure surface, that invertibility that we talked about. Again, here's another reminder of relative vorticity, and we're going to insert our geostrophic wind into the equation. We did this last time as well, and now we have geostrophic relative vorticity. I've written it with this Laplacian. All I've done here is pull out the double derivative. You see that ddx, that's a double with respect to x. dy, double with respect to y. That's a Laplacian. And I've pulled out that 1 over f naught because that's a constant. That upside down triangle, the del operator, with the superscript 2 is the Laplacian. Okay? The subscript p means that the horizontal derivatives are done on pressure surfaces, constant pressure surfaces. So like 500 millibars, 250 millibars, 100 pascals, etc. 100 pascals would be really, really tiny. All right, our QG vorticity equation from last time is this. That would be the advection. I've written a little bit differently, but here's our advection of geostrophic vorticity, so relative and planetary, by the geostrophic wind. And then that stretching term. We can insert our definition for geostrophic relative vorticity into this area right here, and we get that. And then we can switch the order of differentiation on the left-hand side, which is valid for smooth functions, which the atmosphere is, and we get this. That's a start. But we still haven't used the conservation of energy equation. We've used conservation of mass, we've used conservation of momentum, but we haven't used conservation of energy yet. We know that energy is conserved, right? Note that this term in parentheses on the left-hand side, this one right here, that is the geopotential tendency. Change in geopotential with time. Some books use chi, that's like that weird looking X, the Greek X, to represent geopotential tendency, that ddt of the geopotential. We will use it later. For now, I'm going to keep writing it out, but you will see it later. It just means that. All right, QG thermodynamics. We're going to use conservation of energy. Yay. Hydrostatic balance comes from the conservation of momentum, but thanks to the ideal gas law, it's related to temperature. Here's how you get temperature from the ideal gas law. You can go through those steps if you want, but here's how you get it. Now we need a tendency equation for temperature by taking the material, the complete derivative, of the ideal gas law. So you can make that doing this, and then we can use the first law of thermodynamics, which is this equation here, to replace that second term on the left-hand side, this term. First term, this one, and we're going to replace it with that. And we're going to do some more substitutions. I'm going to go ahead and assume that you guys don't care about this part as much. Again, I've already gone over this. When we did QG omega last year, these slides are, well, they are identical. I copied and pasted them, okay, from last semester. All we're going to do is the exact same steps, except when we get our two equations that we can use with two unknowns, two equations, instead of solving for omega, we're just going to solve for geopotential. All right, alpha is the reciprocal of our density P, so we're doing some more changing around of the equations. And so far, this whole thing's been a material derivative, okay? So we're going to expand it into Eulerian form. Here's how you do that. If you need help reviewing that, just let me know, but I feel like we've gone over expanding from Lagrangian to the Eulerian enough that hopefully this doesn't look Greek to you, even though it has Greek letters in it. Combine our two terms containing omega, and we get this. Sparing you the proof yet again, you can express this in terms of a stability constant we call sigma, which is this. It's constant for the troposphere, so I did call it a constant. Here's that relationship, and then this is the conservation of energy form that we need. You see, we just have one term with omega. We have dt, that's temperature, dx by the un's, that's the u advection of temperature, the v advection of temperature, and then here's our tendency part. How is temperature changing with time? To make it QG, we just need to change our advection terms to to make them geostrophic advection terms. So instead of them being affected by the total U and the total V wind, it's just being affected by the geostrophic U wind and the geostrophic V wind. Now, if we remember the relationship between temperature and geopotential, we can insert it into this equation, and we get this. So everywhere we had T, I'm just putting this whole thing is, I know it looks nasty, it looks really gross, but we can simplify, and we can rearrange everything, and you get this nice thing. That doesn't look so bad, right? All right, we're good. We have an equation for the vertical tendency of geopotential in terms of geopotential and omega. We now have two equations and two unknowns, omega and geopotential. We can solve for either of them. Last semester we solved for omega. I'm not doing that again until, I guess, 2 weeks from now, in which case I will, I guess. But right now we're going to solve for geopotential. We haven't done that yet, so something new. I hope you like high school math. We're solving systems of equations, baby. All right. Here's our QG vorticity equation. You remember you have omega and you have geopotential, and we have our QG thermodynamics equations. How can we eliminate the omega term when we add these equations? I can't force you to pause and think about it, but I encourage you to do that. If we take the vertical derivative of the bottom equation and multiply it by F naught over sigma and add it to the top equation, the omega terms will cancel out. So let's see what that looks like. This is what that looks like. So here's our top equation, which is identical to this one. I didn't do anything to the top equation. I only messed with the bottom equation. Here's that. I took the vertical derivative, so now it's a second derivative instead of a first derivative. I've multiplied it by F naught over sigma, so you'll see that F naught over sigma, and here's that vertical derivative on that side. So we're going to add those together, and then look, these terms with the omega, they're identical. They cancel out, so they're gone. So we get this equation, and that's only in terms of the geopotential, so that's why we did that. So we can multiply through by F naught just to make things simpler and reorganize things, and we get this. This is the equation. It's 3D Laplacian of geopotential tendency. It's equal to the advection, here's that UG, of geostrophic absolute vorticity, and then subtracted from the differential temperature advection. So that's that DDP. DDP is up in the atmosphere. That is differential temperature advection. You still see that UG by the geostrophic wind. That's how we know it's advection. We're going to talk about this a little more. So again, don't freak out if you don't understand everything yet. It's okay. I'm not going to make you do it quantitatively yet again. Another form of this equation, remember, here's that chi. That's just that's just chi. Change in geopotential with time. That's chi. I've just rewritten it. So here's how you can rewrite that. Means the same thing. Our 3D Laplacian, so x, y, z, those are our three dimensions, or x, y, p, depending on what vertical coordinate you're using. That's equal to the advection of the geostrophic absolute vorticity, that means relative and planetary, minus the differential temperature advection. And then I've also added two extra terms in here. I've got friction in here, that's this term, and the differential diabatic heating, that's this term. We're going to talk about this expanded equation, but many, many times you're going to neglect these last two terms, which is why I didn't have it in this equation. But I've put them in here because we'll talk about them very briefly, but you're very likely never going to use them, and we'll talk about why. So, the left-hand side of the equation first. This is the left-hand side. The left-hand side of the QG geopotential tendency equation is proportional to negative chi. So, when the right-hand side of the equation is positive, chi is negative. So when the right-hand side of the equation is positive, what we're seeing is a local decrease in the geopotential height with time on a given isobaric surface. If the right-hand side is negative, then chi is positive, which means an increase in geopotential height with time, again, on a given isobaric surface. So what you'll see is in our full equation, a lot of these have negatives in front of them, right? That has a negative, that has a negative, that has a negative. So when we talk about terms specifically, you'll see me say that it's proportional to chi. That's because I'm multiplying both sides by a negative. So then this term positive is equal to chi because this side of the equation was negative chi. If I multiply both by a negative, they're both positive. So let's talk about geostrophic vorticity advection. That's that first term. Okay, this term right here is our geostrophic vorticity advection. That one did not have a negative in front of it. So you'll notice that now it does. There's that negative out in front so that it can be proportional to chi so that we know whatever the sign of this is, that's chi. We don't have to do any extra math, right? Okay, this is depicting the advection by the geostrophic wind, note that subscript of G, of the relative and planetary vorticity. Relative and planetary vorticity. The cyclonic geostrophic vorticity advection is given by this. If it's greater than 0, that's cyclonic because it will be positive, and that's, cyclonic in the northern hemisphere. So F naught is always positive in the northern hemisphere. So cyclonic geostrophic vorticity advection on an isobaric surface results in chi less than 0. So let's think about this. I told you that this is greater than 0. I probably should have gotten rid of that negative sign. Again, I'm sorry. Ignore that negative sign out in front and the F naught. Just this part, this inner part, that should be greater than 0. F naught's positive, but then we have this negative, which makes that whole thing negative, so chi would be negative, and that's a decrease in geopotential height with time. I will also fix that. Sorry. Anticyclonic geostrophic vorticity advection, again, ignore this part outside of the parentheses. We're only looking at the part inside the parentheses. That's negatives, less than 0. But again, F naught positive, and we have this negative, so we have a negative times a negative. That's positive, so chi's positive. So anticyclonic geostrophic vorticity advection on an isobaric surface results in chi greater than 0. That's a local increase in geopotential height with time. So the things in bold here are the important parts, right? Cyclonic geostrophic vorticity advection results in a local decrease in geopotential height with time. Anticyclonic geostrophic vorticity advection results in a local increase in geopotential height with time. We're going to talk about why in a minute, but still talking about that. Geostrophic vorticity, relative vorticity, is maximized at the base of each trough. We talked about this, right? It's most cyclonic at the base of each trough. Therefore, we have westerly geostrophic wind at the base of the trough, resulting in height falls to the east and height rises to the west. So anticyclonic advection to the west is height rises. Cyclonic advection to the east, height falls. Geostrophic relative vorticity is minimized at the apex. So we have anticyclonic vorticity at the top of each ridge. So we have height rises, anticyclonic advection to the east, and height falls, cyclonic advection to the west. The important thing here is geostrophic vorticity advection does not change the trough ridge amplitude most of the time. There are some key cases in which it can. You can refer to Lackman's textbook for that, or you can email me if you're curious. But it does almost always result in the movement of the trough ridge pattern. The movement across the continent, the world, that's what the geostrophic vorticity advection is important in. So let's talk about this, all right? We got a ridge trough pattern here. Here's a ridge, here's a trough, here's a ridge. This is an idealized advection, or idealized example. I'm so sorry. Anyway, so we have cyclonic vorticity here. So where is cyclonic vorticity advection happening? Not right here. This is where it is. This is not where the advection is happening. Okay? Advection is happening downstream of it. So we have high values of geostrophic vorticity, relative vorticity, moving this way. So here's where the cyclonic vorticity advection is happening, right? When we have cyclonic vorticity advection, we have height falls, all right? That height is falling. So what's happening is this part of it, this part of the curve where that's happening, it's starting to mirror this, right? So this trough is moving to this area. You can picture like another trough forming. But what's happening on this side? Well, we have anticyclonic, which means it's negative, and that's being blown here downstream, right? So this is where the anticyclonic vorticity advection is. And when we have anticyclonic vorticity advection, we have height rises. So that ridge is moving here. So now we have a ridge here and a trough here. You see how that's moving it downstream? I hope so. Otherwise, I would draw on the board if I was in class. This is, again, an idealized example. And in the real world, geostrophic vorticity advection can, in fact, result in amplification or de-amplification of that trough ridge pattern. But in general, the geostrophic vorticity advection term is chiefly responsible for the trough and ridge movement, as I've just shown you. All right. So let's talk about the next one. Differential potential temperature advection. So that term inside the parentheses right here is the geostrophic advection of potential temperature. It's encapsulated in a partial derivative with respect to pressure. That's this one. Therefore, it's differential potential temperature advection. That's the differential part, is that DDP. So if we have to see how it's varying in height, that means we have to look at isobaric levels both above and below the level on which the equation is applied. So if we're looking like 500 millibars, right, we want to know what is the differential temperature, blah, 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 blah. What is the differential potential temperature advection of at 500 millibars? We want to look at the temperature advection at 250 millibars and at 700 millibars. Does that make sense? Hopefully. If there's warm potential temperature advection, so positive potential temperature advection, then that term inside the parentheses is greater than 0. If it's cold or negative, then it's negative. In order for the trough or ridge to change, it has to be 0 for that amplitude to change. If it's 0, it's not going to change. All right. So if potential temperature advection is becoming more positive with increasing height or decreasing pressure, right? Because decreasing pressure as we go higher in the atmosphere. If potential temperature advection is becoming more positive with height, there's two ways that could happen. Warm air advection increases in magnitude upward, or cold air advection decreases in magnitude upward. So either warm air advection increases in magnitude as we go up in the atmosphere, or cold air advection decreases in magnitude as we go up. Either one is going to result in a positive potential temperature advection. Change is positive, so chi would be less than 0, which would lead to a local decrease in geopotential height with time. The potential temperature becoming more negative with increasing height and decreasing pressure. That's that key part here. We had change is positive, but pressure is decreasing. That's what made that negative, chi negative. You didn't catch on, but this part again, we had negative. This part in the parentheses was negative, but we have it in with respect to pressure, which is also negative as we go up. So that makes it positive. The chi is positive, which is a local increase in geopotential height with time. Okay, so that's warm air advection decreasing in magnitude as we go up, or cold air advection increasing in magnitude as we go up. Okay, let's look at an example. Here we have warm air advection decreasing in magnitude upwards. That means chi is positive, right? Warm air advection decreases in magnitude upward. Chi is positive. That's an increase in geopotential height with time. Cold air advection decreases in magnitude upward. That's positive potential temperature advection, which means chi is negative, which is a decrease in geopotential height with time. Okay, so let's think about this. At the left, right, our 500 hectopascal height, right? That's increasing more due to the increased thickness below it than it decreased due to the increased thickness above, right? Because thickness above, they're both getting thicker, right? Warm air advection makes the layer get thicker. So you can see those black arrows, like if you want to draw thickness lines on either side, it's getting thicker on both sides, but it's getting thicker more at the bottom, right? So increased heights. Okay. The right 500 hectopascal height decreases more due to the decreased thickness below right? So here's our new thickness, less, versus our old thickness, which would have been like, so new thickness, old thickness. Here was our old thickness, new thickness, right? So on the right-hand side, right, we have our new thickness here, which is less. And then it decreased more below than it did above. So we have height falls, right? It's going down at 500 millibars because of thickness, right? Because our thickness below decreased more than it did above. So we have height falls. Does that make sense? Imagine if you're standing on a platform and you have two springs pushing on you at equal strength, and they both weaken at the same time, but one of them weakens more. You're going to go towards that one, right? That's all I'm saying. So same thing with warm air advection, right? If you have two springs pushing against you and they both get, besides you getting squished, they both increase in strength, but one of them increases in strength more, you're going to go in that direction. So if you have warm air advection increasing more here, and that's going to push you this way. And if you have cold air advection decreasing more here, you're going to get pushed this way. Does that make sense? I hope so. It's a little weird to think about. But you have height rises here and height falls here. And I think you can kind of see that with the arrows, right? All right, friction. Moving on, finally. K is the effects of friction. That's K right here. It's always positive. Friction's not negative. It's only not zero when in the boundary layer or close to the surface where friction effects can take place. Since it's positive, chi, therefore that x, is going to have the same sign as our geostrophic relative vorticity. So in the base of a trough where we have cyclonic geostrophic relative vorticity, which is positive relative vorticity, chi is positive, which means we have a local increase in geopotential height with time. At the ridge, we have a local decrease because we have anticyclonic geostrophic relative vorticity, which is a decrease in geopotential height with time. Friction, that K, that's going to act as a brake on the intensity of troughs and ridges, right? Because it slows down the wind speed, so it's going to slow down the intensity. It's going to decrease the intensity. All right, our last one, I think, yeah. Differential diabatic heating. DDP here is our differential. dQ/dt is our diabatic heating rate. If it's positive, we have diabatic warming. If it's negative, we have diabatic cooling. It's only not zero when there's diabatic heating. If there's no diabatic heating, then it's zero. It's also encapsulated in that partial derivative with respect to pressure right here. So it's a differential. How is that changing with height? If it's becoming more positive with height, increasing height or decreasing pressure, then our change is positive, but our pressure is decreasing, so chi is negative. That leads to a local decrease in geopotential height with time. If it's becoming more negative with increasing height, then change is negative, so chi is positive, right? So that's an increase in geopotential height with time. All right. Hopefully that makes sense. Read these a few times if you don't get it, and if you still don't get it, email me. So, why are we even here? Why are we here? Just to suffer? Yeah, kind of. But not really. But sometimes. Another equation? Catherine, why are we doing another equation? You've already given us like 16 million equations. Yeah, I know. But I mean, listen. The QG height tendency equation incorporates those underlying physical forces that are going to lead to changes in geopotential height, right? It also includes friction, which our other equations didn't have. So it gives us a more complete view of the atmosphere. We get the surface effects too. And this equation is unique because we can use it to explain the evolution of troughs and ridges, right? It's not that a trough is being blown or a ridge is being blown, right? It's really more that one's weakening somewhere and it's strengthening somewhere else, and the ridge is weakening somewhere and strengthening somewhere else. So it's more like it's decaying and reforming because of our advection. So how do you use it? how do we evaluate this equation, Catherine? Like, you're gonna give me a homework, and what am I supposed to do? Like, am I supposed to calculate? No. No, you don't. You don't calculate it. And I'm not even kidding. You really don't. You will never be asked to calculate this, probably ever. Why? Because we have a derivative with respect to time. Sorry. Why not, right? We'll get there. Well, why do you think you should, right? We have that derivative with respect to time, which means we should be able to predict it, which means we should be able to calculate it, but we can't because we have a second derivative of chi. That local geopotential height tendency depends on the value at locations around it and above it and below it. So we need an iterative approach that's really, really hard to code. And it's really, really expensive, like computationally expensive to execute. And even if we could do that, it's still really hard to accurately calculate the frictional and diabatic heating terms. So it wouldn't even be that good of a calculation, even if we could calculate it. So, well, Catherine, why the hell did you just spend almost 30 minutes talking about this if I can't even plug and chug? Because we can still diagnose the evolution of the tropospheric height field with time using this equation. Not quantitatively, but qualitatively. Geostrophic vorticity advection, differential potential temperature advection, we can look at those on models. You could pull up College of DuPage and look at those fields. And so you can use it qualitatively to figure out this kind of stuff. That's why I did it, okay? I better see it in some of your forecast discussions if it's relevant. That's it. Enjoy your snow day. Get out of here. Log off. I'm going to log off because I can see the moon and I'm hungry. Okay. Goodbye.